Hey, welcome to Differential Equations. This is the first section. I'm using the Zill book. And so as soon as we get my... Here we go. Okay. So start with just defining what a differential equation is. So, equation. It's an equation that contains derivatives of one or more functions, and basically what you're doing is solving for kind of the original function. Okay, so it's an equation that contains derivatives of one or more functions. And we've seen examples already. The connection between integration and differential equations is, close. They're closely related. So whenever you figured out an antiderivative, you are essentially solving a differential equation. Okay. So for example here, y prime equals 2x is a differential equation. And to find the solution, you would just basically integrate. So you could guess you go down here and 2x dx. The integral of that is 2x squared over 2 plus c. We'll just say 2x squared plus over 2, so x squared. So one particular solution would be x squared, and later on we'll talk about particular solutions versus general solution. A general solution will have the plus c thing on it. Okay, so there's very basic differential equations. We'll look at more complicated versions of that problem. So here's another differential equation that you could probably solve if you just played around with it enough. And all it's saying is that the second derivative is equal to a negative of the original function. So you think about kind of your list of functions, what would actually work there? Well, sine x I think would work as a solution. Y equals sine x, the derivative would be cosine x, and then the second derivative would be negative sine x, and because y is equal to sine, that's equal to negative y. And this is just another way of stating this differential equation. In this class, we'll develop methods for solving differential equations. Guessing is one way to do it, but in general, we'll have some sort of algorithmic type methods that we'll be able to apply for different classes of different differential equations. Okay, so speaking of different classes, or in this case types, we want to dissect the set of differential equations into two types. The first type that we'll look at, the type that we are most interested in, are the ordinary differential equations. I'll just say ODEs. And in this case, we have one independent variable. So if you took Calc 3, you're not going to see any like multivariable type problems. It's always one independent variable. So that being said, you can have more than one function, but you can't have more than one independent variable. So one independent variable. Some examples, I think I just took these from the book, but dy over dx plus y equals e to the x. So the independent variable here is x, right? And the function is y. Another one, dy over dt, so the derivative of y with respect to t, plus the derivative of this other function, we'll call it x with respect to t, equals 2x plus y. So here, one independent variable is the t, but you have two different functions, the y and then the x. Okay. Sorry about my x's, pretty nasty. The other type of differential equations, which you'll hopefully study later on, are PDEs, partial differential equations, and in these cases you'll have two or more independent variables. And the big red flag is that you'll see the weird curly D instead of our usual. Let me use a different function, not y. Let me use u just to be consistent with the book. So the partial derivative of u with respect to x plus the partial derivative of u with respect to y equals 0. So partial derivatives you would have seen in Calc 3 if you took it. If not, it's not a big deal, and I'll sort of introduce a quick introduction to those, I think, in the next video. Okay, but it's pretty simple. It's basically all the derivative rules work the same. It's just instead of so for example, I'll let the cat out of the bag here. If we have a function f of xy equals 3x plus 2y, and you want to take the derivative, the partial derivative of f with respect to x, it would look like this. And what you do is kind of just pretend y is a number, like a 5 or something. So it'd really just be like taking the derivative of 3x plus 2. And when you take the derivative, you'll just get 3. The derivative of 2y will be 0. Okay? And then you could also find the derivative with respect to y. So this time the x is a constant, so the 3x would just be the derivative of that is 0 with respect to y. And then the derivative of 2y would just be 2. Okay? So hopefully you've seen that in Calc 3. If not, I'll sort of give you a gentle introduction to that more in the next video. Okay? But it's no big deal. All right, one thing to note here is the notation. So when you see this dy all over dt, this means the third derivative of y with respect to t. This notation here is the Leibniz notation. There were two calculus gurus, basically Leibniz in Europe and then Newton in Britain. And Leibniz used this notation. The other notation that we'll use in the book is the prime notation. The disadvantage of the prime notation is that you can't see the variable that the derivative is taken with respect to. Okay, so bummer. But for ODEs, it's fine. Okay, so anyways, there's that. The book also notes Newton used little dots over his for his derivatives. I've never used that before, but okay. Section 3, what is the order of a differential equation? That's just going to be the highest derivative present in your equation. So for example, here I have the second derivative of y with respect to x plus the first derivative of y with respect to x plus y equals e to the x. Okay? This is going to be a second order differential equation. And it's actually linear, and we'll talk about linear, nonlinear here in a second. But anyways, that's second order. Another example, and this one may be kind of weird. It's nonlinear. I'll talk about what that means in a second. But anyways, the second derivative of y with respect to x equals the square root of 1 plus the derivative of y with respect to x squared. So that just literally means dy over dx times dy over dx. It's not in order. So the highest derivative in this case is going to be from this, the second derivative here. So again, this will be second order. Okay. One other form that will come up that's kind of weird whenever you see it is the differential form. And you may have seen this like in Calc 1 where, or even in Calc 2 where you're doing your u subs. You let u equal 2x, and then the differential form of the derivative is du equals 2x dx, okay? As opposed to writing du over dx equals 2. Whoops, that's the derivative of 2x is 2, sorry. Right. So this is that differential form, and we'll see this form in first order differential equations as well. You may have already seen these in Calc 3 if you took that, but the generic example, m of xy dx plus some other function of x and y dy equals 0. Okay, let's look at converting into this general form. So we'll look at example 2 from the book. And we have y minus x dx plus 4x dy equals 0. So I want to get into a more standard form like what I see above with the dy over dx. So very simply, you could divide everything by dx. And you get y minus x plus 4x times dy all over dx equals 0. When you have an entire differential equation equal to 0, so you have everything on one side and 0 on the other, the book is going to call that the general form. And that's one form we would like to have. The other form is called the normal form. And what you do there is get the highest order derivative and put it on one side and put everything else on the other. So let's see if we get the normal form. I'm going to move the x and the y over, so I have positive x minus y. And then I could divide both sides by 4x, and I should have my normal form. Okay, so this is the normal form. And by no means do you need to memorize these terms. I will probably not use them very much myself. Let's look at example 3, part B. Y double prime minus y prime plus 6y equals 0. This is our general form. To get in the normal form, you need the highest order derivative on one side. So I'm going to put the y double prime over here and then move everything else to the other side. And there it is. Okay? No big deal. For some techniques we use in solving differential equations, you're going to want the normal form. For others, you'll want that general form. Okay. Okay. Finally, let's talk about linearity, or linear versus nonlinear. And people have told me that in the real world you get more nonlinear than linear. It's almost like linear is too easy, too simple. It's like when you're doing your homework and all your answers are big long decimals as opposed to just integers. I don't know. But anyways, let's introduce the linear nth order differential equation and see what it looks like. Oops, ODE. So it's going to be a bunch of derivatives, and then the coefficients on the derivatives are going to be functions of the independent variable. So for example, some function a sub n of x times the nth derivative of y with respect to x plus some function of x times the n minus first derivative of y with respect to x, on and on and on, all the way down to a sub 1 of x times the first derivative of y with respect to x, plus a sub 0 of x times plain old y, and then maybe you'll have some function of x on the other side. Okay. Okay, so that's linear. If it's not linear, if it doesn't have that form, then it's nonlinear. Okay. And some examples from the book of nonlinear guys, something like 1 minus y times y prime plus 2y equals e to the x. So this is nonlinear because the coefficient on y prime is not a function of x. Okay, it's a function of y. Let's look at another second derivative of y with respect to x plus sine of y. Again, you can't have a function of y or any of the derivatives. They have to kind of just be factors of themselves, right? So having sine of y is bad news, and that's going to make it nonlinear. Another one, the example I showed you above is also nonlinear, because we have this function of the derivative kind of sitting inside the square root. Okay. So all those are nonlinear. Let's talk about solutions to differential equations. So, in solving just algebraic equations like 3x plus 1 equals 5, all you're looking for is a number, right? Maybe worst case scenario, you'd have an inequality back in algebra and you'd have to find like an interval of solutions, right? Now we're looking for functions that are solutions to the differential equations. And along with functions, you have to worry about domains. Okay, so it gets a little bit annoying in that regards. So let's take a look. The function, you can use phi of x for the solution. You can use y of x. It just depends on what variables you're working with. Phi of x, though, is like generic. Phi of x is a solution on the interval I, which we're going to call some interval of definition, to an nth order differential equation. If the following three criteria hold. First, the solution has to be defined. It has to be defined and have derivatives. If you remember your calculus, if something is differentiable, it's therefore continuous. If it's continuous, it's not necessarily differentiable, that stuff. So anyways, if phi has derivatives, then phi is continuous on the intervals such that it is differentiable. But anyways, we need phi of x to be defined on I, and then we also need phi of x to have n continuous derivative as n continuous derivatives on I. So it's an nth order differential equation, so we need the n derivatives. And then thirdly, phi of x has to satisfy the ODE. For every x in I. Okay. So the idea of satisfying means basically when you plug it in and all the derivatives, you can get the right side of the equation to equal the left side of the equation. It's a bit like checking your solution back in algebra. So maybe you'd have 2x plus 5 equals 3, and let's 7, right? And then we think the solution is x equals 1. So to show it's a solution, you plug it into the both sides. In this case, it's only the left side. You get 2 plus 5 is 7. So 7 is 7. So that satisfies the original equation, and therefore it's a solution. Okay. Okay. So anyways, there's that. I'll just note here, I is called the interval of definition. They have other terms for it, but that's what I'm going to call it. Okay. Okay. So, anyways, let's work with this last point, just showing that a solution satisfies the ordinary differential equation. I'll look at example 5, and we have show the function as a solution, right? Show the function satisfies the ODE. Okay, so let's look at part A first. We have the differential equation dy with the derivative of y with respect to x equals xy to the 1/2. And then they're going to give you a solution, y equals 1/16 x to the 4th. Okay, so the way the book does it, I'm not a fan of it, but I'll try to keep with the way the book does it. So they want you to work with the differential equation, work on the left-hand side, and on the other side of your paper, work on the right-hand side. This is how I want you to do it on the test, too. The way the computer does it is a little weird when you do your homework in the computer. But anyways, in order to pull this off, you need to kind of work with the solution and get the number of derivatives for the order of the differential equation. So that, for example, this differential equation has order 1. I'm going to need the first derivative. Okay. So the first derivative, bring down the 4, subtract the old exponent by 1, so you get 1/4 x cubed. And then you just kind of consider the stuff in that box the given information. Okay? And you could use this in your kind of quote-unquote proof down here. Okay, so I have the left side. I'm starting on the left, so the left is circled in red, just this thing. Sometimes it's more complicated, not this time though. So I have dy over dx, and then I use the stuff in the box to rewrite it. Okay, so in this case, dy over dx from the box is 1/4 x cubed. Okay. So let's look at the other side. The other side, let's circle it in yellow, I guess, is this thing. So I have xy to the 1/2, and now I use the given information to rewrite it, and hopefully I'll get the left side. Okay, so I'll have x times y, which is 1/16 x to the 4th, which would the x there, to the 1/2 power. Little bit of algebra here. So x times 1/16 to the 1/2. It's basically just the square root of 1/16. Whoops. 1/2 times x to the 4th to the 1/2. Right? So I have x times 1/4 times the square root of x to the 4th. So you can figure that out just by rewriting x to the 4th as x squared squared. And then recall that if you have the nth root of something raised to the nth power, and that nth power is even, that's equal to the absolute value of whatever is being raised to the nth power. So here I have, down below here in my work, I have the square root of x squared raised to the 2nd power. So I can simplify that into the absolute value of x squared. Okay. Anything squared is positive, so you don't need the absolute value. So you can just write it as x squared. And then finally, you get 1/4 x cubed, which is basically the left-hand side. Hence, it works on for any real number x. So it satisfies. Let me think how I'm going to write this. This works for all x in the interval from -infinity to infinity. Sometimes it won't satisfy. It won't work for all x. Like you'll have maybe some restriction due to division by 0 or something weird. But in this case, it worked for all. Let's look at one more, part B here. So we've got y double prime minus 2y prime plus y is 0. And then they say the solution is x e to the x. Okay. Okay. So again, I just want to show that this thing satisfies the differential equation. Again, I'm going to build up to the order of the differential equation. So the first derivative, I have to do a product rule. So derivative of x is 1, e to the x, plus leave x alone, and then derivative of e to the x is e to the x. Second derivative, derivative of e to the x is e to the x, plus the derivative of x e to the x, you've got to do product rule. So leave e to the x alone, the derivative of x is 1, so 1 e to the x plus x, derivative of e to the x is e to the x. Simplify that thing, 2 e to the x plus x e to the x. Okay, so that's my given information. I want to use that to get the sides to equal each other. So on the left side, I have y double prime minus 2y prime plus y equals, and then I'm going to plug in this junk. So the second derivative, 2 e to the x plus x e to the x minus 2 times e to the x plus x e to the x, and then plus x e to the x. And that equals 2 e to the x plus, there are 2 of those, plus 2x e to the x. Distribute. Minus 2 e to the x minus 2x e to the x. And then 2 to the x minus 0. No, it's just 0. Okay. So it's the left side. The right side is just plain old 0. So they're both the same. We didn't do any fancy footwork, so it'll work for all real numbers. So it satisfies the equation for all x in the interval negative infinity to infinity. Maybe I should say satisfies the differential equation. So I'm going to want you to do it like this on the test as well. Okay. Okay. One thing that's kind of weird with this now, you have to deal with the domain of the function and this interval of definition, and they may not necessarily be the same. So, warning, domain of the solution v of x and the interval of definition I may not be the same. The book gives you like a visual picture type problem here. So let me set up the differential equation for that. Xy prime plus y equals 0. Their solution, y equals 1 over x. Okay, so the domain of this thing, and we'll just assume it satisfies the differential equation. You could check on your own if you want, but the domain of y equals 1 over x is all real numbers except 0, right? So the domain is going to be negative infinity to 0, unioned with 0 to infinity. The interval of definition is different. We need the thing to be differentiable on the entire interval that we're working with. So you can pick one of these intervals from the domain, or you can pick like a subinterval from one of these intervals. Okay. So anyways, y equals 1 over x needs to be defined and differentiable. And then y prime, which is negative 1 over x squared, needs to be continuous. Okay. So if you pick the domain, well, first off, the derivative is, there's no way it's going to be continuous. So you can't just pick the domain. So we have to restrict the domain. You can pick either interval. If it's an initial value problem, you just pick the interval with the initial value. But in general, rule of thumb, they want you to pick the rightmost interval if they're both kind of the same. So we're going to pick 0 to infinity for our interval definition. And then the function will be defined there, and its derivative will be continuous. So if you know rational functions are continuous everywhere, the denominator is non-zero. Okay. Let's look at this next example. I took this problem from the book. This is also going to be our video quiz. So the video quiz is just me making sure you're watching the videos. And so I don't have to worry about explaining to you something that I already explained in the videos because you're not watching the videos. So anyways, this is the video quiz. So what you do is kind of just basically copy it down. I'm not asking you to do any thinking really. Just copy it down and put it on a piece of paper. You'll probably turn in the first 3, 1, 1, 1, 2, 1, 3 all together and send it to my email. So you basically write it out in your hand. Take pictures or scan it, turn it into a PDF, and then send it to my email. So turning something into PDF once you have, so let's pretend I've already uploaded my picture and I want to turn it into a PDF. So how do I do that? Well, you go to Microsoft Word, you go to Insert, and then go find wherever you stored your pictures. So maybe this is the picture of your homework. And then you'll hit File, Save As, Browse, and then down here, you can call it whatever you want, but go to Save As Type, and then you should be able to scroll down to PDF, and it should allow you to save that as a PDF, okay? Okay, I'm not going to say that. That's the idea. Okay, so without further ado, here I want you to find and compare and contrast the domain of the solution to the interval of definition. So I have y minus x, y prime equals y minus x plus 8. And then our solution is given as phi of x equals x plus 4 square root of x plus 2. And so I need a domain of phi, and then the interval definition, just put I. Okay. Okay, so for the domain, looking at this function, the domain will be an issue whenever you have division or a square root or a logarithm. That'll affect that stuff will affect the domain. So here I have a square root. I need to make sure the stuff inside the square root, namely x plus 2, is greater than or equal to 0. So I need x to be greater than or equal to -2. So the domain is going to be square bracket -2 to infinity. Okay. For the interval of definition, again, you need two things. You need phi of x to be defined. And secondly, you need its derivative to be continuous. So this is a first order differential equation. I need phi prime of x to be continuous. And so what is phi prime of x? So phi prime of x equals, so if we rewrite phi of x above here as x plus 4 times x plus 2 to the 1/2, I can do a power rule. First, the derivative of x is 1 plus 4. Bring down the 1/2 exponent, and then you have x plus 2 to the -1/2. Rewrite that as 1 plus 2 all over the square root of x plus 2. And yeah, now you kind of just, where is this thing continuous? And you see there's an issue, right? There's an issue now at 0 because you can't have this denominator equaling 0. So on the left there, you have x plus 2 greater than or equal to 0. Now you need to set x plus 2 strictly greater than 0, and then solve. X needs to be greater than -2. So the interval of definition then, instead of square bracket, would be open bracket -2 to infinity. But you can't have -2 because you can't have division by 0. Okay, let's move on to implicit and explicit solutions, so section 7. Okay, so explicit is pretty much what you're used to. What you would put into your calculator, if you graphed it, you have that y equals menu and the TI-84s and stuff. Those are explicit functions. Okay, so y equals some function of x is explicit. So for example, from above we had that function y equals 1/16 x to the 4th. We also have y equals 1 over x. Those are both explicit. Implicit are functions that you kind of either can't get it into that form, or if you did get it into the form, it would just cause a headache, right? So the easiest example you can think up is the equation of a circle. Okay, and the book will walk you through kind of checking that as a solution. I won't be expecting to do that, and the homework doesn't either, so you can just read that example in the book on your own. Okay, but that would be, this is an implicit version. You can get the explicit solutions, but it turns out working with square roots is just so nasty that you tend to avoid it. And just working with this thing alone is almost better. Okay. All right, so anyways, let's move on to my next section. We have particular, general, and singular solutions. Okay, so this is what I was talking about way back at the beginning of my notes, right here. Okay, so there's a solution right here. This x squared is a solution to the differential equation y prime is 2x, but there's other solutions, right? There's x plus 1, x plus 2, x plus 3, et cetera, et cetera. So let's come back down here. Example, again, I'll just use y prime equals 2x. So I got a mistake in my notes. The antiderivative of y prime, or if you did the integral, you would get y equals x squared is one solution. But other solutions, y equals x squared plus 2, just y equals x squared plus anything, right? These are all general or particular solutions. Okay. But you know, the thing you get from the integral, if you did the integral, you get x squared plus c. You always have to tack on that constant. That's the general solution. And from this general solution, you're supposed to be able to get all these particular solutions. If there's a solution that you can't get from the general solution, they'll call that a singular solution. Okay? And you can usually find those just by inspecting the differential equation. But let's, just for example, let me show you the singular. We have something like dy over dx equals xy to the 1/2. So this is basically the differential equation I had back here in example 5, okay, that thing. It's just now I'm going to give you the general solution and show you that a particular solution, one of the particular solutions, you cannot get from this general solution. Okay. So from above, the particular solution of 1/16 x to the 4th, that thing I can get by letting c equal 0. So if you let c equal 0, you get y equals 1/4 x to squared plus 0, but you know, and that would be the 1/16 x to the 4th. And that's the solution that's given in this example we were playing around with up here. Okay, so 1/16 x to the 4th. But there's another solution that you can't get by just letting c equal something. Okay, so notice, note that y equals 0 is also a solution. Sorry about my handwriting. Okay. And let's prove that it's a solution, right? So let's go ahead and do the left hand, right hand stuff for this. So sort of listening to my message downstairs. Let's set it up there. Okay, so first, it's a first order differential equation, so I get the derivative of y. The derivative of 0 is just 0. And then I go left side, right side. So here's my left. I'll put my right way over here. So on the left side, the dy over dx from my given information in the box is just going to be 0. Okay. And then my right side is xy to the 1/2. And then using the given information, you can replace y with 0. 0 to the 1/2 is just 0. And anything times 0 is 0. Okay? So both the left and right work, and it works. So hence, h equals 0, or y equals 0 rather, is a solution for all x in negative infinity to infinity. So you really could not get that from that general solution. Again, you can't get it from here. But I think if you just look at the differential equation, you can kind of guesstimate that is actually one of these singular solutions. Okay. And that'll work, you know, in general if you have something like dy over dx equals x cubed times y minus 3. In this case, you would have a singular solution, I believe, at 3, right? Or I guess sometimes they just call it a trivial solution. And if you put it in there, you'll see that the left side would be 0, and then the right side is also 0, so it works. Okay, but usually you can just kind of see them and pick them off. Anyways, that's about it for that. Let's dive into my math lab or whatever, WebAssign. Kind of see what we're dealing with here. So let's try to maybe practice one of these. Okay, state the order of the given differential equation, blah, blah, blah. Okay, so the order is the highest derivative. This is another way of writing derivatives when you start dealing with higher orders. So instead of putting like 5 tick marks, what's happening here, let me move my notes over so I can, and of course it's hidden in my homework. Okay, so you see they have t to the 7th and y to the 5th. It's the 5th derivative of y is what they mean. So rather than writing out prime, 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 prime. Just put a 5 up there in parentheses. Okay, so the order of that thing is 5. And then it is linear, because all the coefficients are in terms of t, and we're not doing anything crazy to the derivatives or the y. Okay, so let's see if I get it. Yay. Okay, so a bunch of those. Did one like that, one like that. This is their attempt to kind of give you one of these, prove that the solution satisfies the differential equation. And they don't really do here's the right, here's the left. Let me give this one from scratch here. Okay, so here's our differential equation. Here's our potential solution. And then the first step, what they're doing is having you get the given information, basically. So y prime is just the derivative e to the negative 4x over 4 is e to the negative x over 4 times the chain rule, so times the derivative of the exponent. Should be negative 1/4. Okay, so that will go in this box. I avoid using those little symbol buttons. If I can, I find shortcuts on the keyboard. So negative 1/4 e to the negative x over 4. And then now what they're having me do is show that the left-hand side is equal to the right-hand side. So the left-hand side is this 4y prime plus y, and they use the given information to rewrite it. So 4 times negative 1/4 e to the negative x over 4 plus e to the negative x over 4. Okay. And then instead of switching over to the other side, all they want you to do is simplify it until you get to the right-hand side. So I can simplify this a little bit. Negative e to the negative x over 4 plus e to the negative x over 4. And then that'll equal the right-hand side, which is 0. So here you're just filling in those blanks. So one thing you can do is kind of copy and paste. So hit Control-C and then Control-V. And then that's maybe a little easier. And then this just equals 0. Grade. Yay. Okay. More of the same business. This one's a little bit different. So let's try this one. This another version. Okay, so whoops, this is one, like the one I did in my notes here. It's almost exactly the same. They really run you up the flagpole. They're going to have you kind of do the left-hand side, the right-hand side. Let's find one that's kind of similar to that, but I don't want to do that one. But yeah, let's try this one. Okay. It's another version. Okay, so I have y prime equals 2xy squared, and then y equals 1 all over 9 minus x squared. Okay, so what they're doing first is having you see that it satisfies the differential equation. So you get the given information, which is basically y prime. So you can rewrite this as 9 minus x squared, so negative 1. Y prime is negative 9 minus x squared to the negative 2 times, use chain rule now, negative 2x, rewrite it a little bit so it's pretty, 2x all over 9 minus x squared. Squared, plop that in. Then you're kind of starting on the right side. This time you have 2xy squared, and you use the given information to rewrite it. So you would have 2x times y squared. So what the heck is y squared? Here's y. So 1 all over 9 minus x squared squared, which equals 2x all over 9 minus x squared squared, which is the derivative, right? So let's out of the way. Okay, so 2xy squared is 2x all over, well, basically the same thing from above. So let's just copy and paste, Control C, Control V. Since left and right hand sides of the differential equation are equal when you do the substitution, so that's all you're doing is showing that the left and right are the same. Then we want to find the domain of that solution. So where is our solution? Our solution y is equal to 1 all over 9 minus x squared. So a rational function is continuous wherever the derivative, the denominator is not equal to 0. So set this thing equal to 0, find where it's equal to 0. Plus or minus 3. So the domain of that solution is negative infinity to negative 3, union with negative 3 to 3, union with 3 to infinity. Okay. So go in here. I'm going to have to get my symbols because I don't know the freaking negative infinity to negative 3. Oops, and it's getting the extra parentheses for some reason. And then I need a set notation, u, and back to negative 3 to 3, and then I u, and then back to 3 to infinity. Okay. And then finally, consider phi as a solution of the differential equation. Give at least one interval. So the derivative has the same domain as the original function. So you're basically left with picking one of these three intervals. And the way they want you to do it is basically to pick the biggest one. But you see they have two that are kind of like the biggest at the end. So what they want you to do is pick the one all the way to the right. So they want you to pick 3 to infinity. Well, I guess it's not. They just say pick one. So if they didn't tell you pick 3 to infinity, but here they're not even giving you that as a choice. So it just says give at least one interval I of definition. So that's going to be the negative 3 to 3. Yay. Okay. Hopefully that'll get you through it. There's some fun puzzle questions down here, 13, 14, but I think that'll do it for me. And I'll see you. Thank you for watching, and I'll see you next time.